Hello everybody, my name's Chris Brown. I'm from Scotland, University of St Andrews, which I think is actually possibly colder than Poland, probably the only place on the planet at the moment that's colder than here. So I'm going to talk to you today about multicore. So we now live in a world where basically the single core chip is dead. This is very exciting, obviously. What I have here is just a picture of a chip that I believe was actually released on Tuesday, so 2 days ago. So this is kind of hot off the press. It's a 100-core chip. So it's a single chip with 100 cores, and 100 general-purpose cores as well, not just lightweight units. It also has enormous amounts of cache, so something like in excess of 40 megabytes of cache. This is absolutely humongous. It also has other types of devices built in. It's got network accelerators, Ethernet accelerators. It also supports quite decent amounts of RAM as well. And this is the reality, as we can see. These kinds of things, this is 100 cores. I'll come back in a couple of years and there'll be 200 cores, and so on and so on. So it's almost too good to be true. But there's a catch. Programming these types of systems is absolutely almost impossible. It's incredibly difficult. I'm sure everybody has at least tried this once. The problem really is that mainstream programming models just aren't geared. They're not designed to kind of scale up to this type of parallelism. I talk about here, just as an example, Erlang has a concurrency model built into it, using explicit things like processes, sending and receiving messages, this kind of thing. This doesn't work. Okay? Firstly, it requires an enormous amount of expertise, requires an enormous amount of experience. Concurrency is not parallelism. You can't write programs that are going to scale to 100 cores using old-fashioned concurrency techniques. It just won't work. And also, these processes are not really that lightweight. Everybody in Erlang says, oh, you can spawn millions of processes and they're so lightweight. They're not. You won't get any parallelism from that. And that's just really the tip of the iceberg. It applies to just about every programming language on the planet. If you look at languages like C, it's the same. If you use p-threads, you're going to have headaches using p-threads after about 5 minutes. And also, applications can be parallelized in lots and lots of different ways. There doesn't exist one implementation of a parallel program. It just doesn't happen like that. If I come back next year and I show you a different chip, you're going to have to completely write all of your code to work with it. You can't just take a program and then it will just run on all parallel systems. It just doesn't work like that. So choosing how to write this parallel code, but also choosing which parallel structure to exploit is very non-trivial. It requires a lot of expertise, a lot of experience. You can do it on your own, but it's going to take you a long time. So you can basically implement all possible parallel programs, but that's going to take you almost an infinite amount of time to implement. So at St Andrews, we've been trying to work at this problem. We've been trying to solve it. So just looking back at Erlang, I just use this as an example to show you what we're doing. We created a library called Skel. This is basically just a library you can use. It applies in other languages. You have similar types of libraries as well. It provides pluggable templates, so parallel patterns that you can just basically plug your functionality into them. So it gives you all of the parallel implementation you need, and you just plug your units of work into it. And as far as we're aware, it's the only library that exists for Erlang. It contains a number of different parallel patterns. I'll talk about these in a moment. It's fully nestable, so you can nest different patterns inside each other, so you can have almost an infinite amount of different types of parallelism. It's kind of like a DSL. So here's just an example at the bottom of the slide here. It works by calling this function do in the module Skel. You give it a description of your skeleton, and you give it some input items. I'll explain that in a bit more detail later on. So the point of this is it encapsulates all of the parallel implementation. So the programmer doesn't have to worry about it. And every time I write an application, I don't write an operating system. So why would a parallel programmer do the same thing? So this is just a couple of examples of the type of patterns Skel provides. This one's called a parallel pipeline. The idea here is you've got some work coming in here. We call them tasks. And then we've got a number of stages. Each of these stages can execute in parallel. So you can imagine you've got, I don't know, n CPUs. Each stage here can execute on a different CPU in parallel. So one way to think about this is like a car factory. These are robots. You've got a robot putting on the door, a robot putting the engine in, and so on. Obviously, each robot can work on a different car at the same time. So that's how the parallelism comes into it. And then down below here is just an example of how this works in Erlang. So you basically call your do function again. You simply pass it a tuple, and this tuple describes what the skeleton is. So this first thing here is an atom. It just says pipe. It's just a label to say we're using the pipeline pattern. And then we simply just pass in our stages as a list. And then at the end, we pass in our inputs, which is a list of work that's going to be executed. Another example is a farm. This is like a data parallel pattern. So here we've got some tasks coming in, and then they all get sent off to different, what we call workers. So each of these workers can run on a different CPU. As you can see here, you get like a replicated effect. So each of these workers are independent operations. And obviously, if you have 100 cores, you can have 100 workers and so on. So you get quite massive amounts of parallelism with this kind of pattern. And of course, you can put pipelines inside here. So I can have a worker that's a pipeline and so on, or a pipeline where each stage is a worker, farm, and so on and so forth. So one other thing I'm going to talk about today is refactoring. So I'm going to combine refactoring and this skeleton approach to show you how you can write parallel programs quite easily. Has anybody heard of refactoring? Quite almost everybody. That's good. Yeah. Yeah. So it's been around for a long time. We all know what this is, right? I mean, it's a semi-automated approach. So I'll just briefly explain it very quickly for those who've never heard of it. It's basically an automated or semi-automated tool that exists in common environments, like you could have Emacs or Clips or whatever. And the idea is you have a menu of different things you can do. Like, here's an example here. So you can do some renaming. You can select a function and give it a different name. And this is not just a simple find and replace. It's a bit more intelligent than that. So what it would do is it would rename all of the different functions that point to that one you've selected instead, and then rename all those. It also does things behind the scenes, so it checks for conditions, so you can't give it, obviously, a name that's not going to be valid Erlang syntax or whatever. You can't give it a name that already exists. The tool won't let you do that. So it's a bit more of a disciplined kind of software engineering tool. So refactoring is generally, they're described in terms of some transformation and some conditions. So the transformation is actually the easy bit. It's just changing the source code. So just making the change. Changing the name of function F to function G. But the actual, the complicated bit behind the magic, if you like, is the conditions. So these are things like, can I actually apply this refactoring? Does it make sense? If I rename a function G to H, is it going to conflict with another function called H? And so on. So we call these the semantics. And you can have conditions, you can apply them before you try to do the transformation. You can have conditions that you apply at the end, and so on. So we're going to use this technology to help people write parallel software. So we developed a refactoring tool for Erlang that helps people introduce and tune parallel programs. So it's quite an easy way to introduce parallelism, just at the click of a button. This is good because obviously you can have a tool that helps you choose the right abstraction, the right parallel pattern. You don't have to really think that hard. If you come along with a new architecture, you just have to click a few buttons and you get a new implementation that's optimized almost instantly. The tool will do all the condition checking for you. It won't do anything stupid. It won't introduce deadlocks, all this kind of stuff, race conditions, all this. It'll all be, it's guaranteed that it will be correct. You can integrate things like performance information. I'll talk about this in a short while. So you know you're going to get the best performance if you choose this pattern, etc. This is just an example of a kind of a screenshot of the tool. This one's in Eclipse. So here you can see you've got your program here. You've got a menu. You can choose different refactorings to apply and so on. And they're all undoable. So they're all, if you introduce something, you can always go back, which is another nice feature of these types of tools. If you make a mistake, you can just revert. So we've built our particular tool into Wrangler, which is an Erlang refactoring tool. It's embedded into a number of common IDEs, and examples here is one's Emacs, another Eclipse. It might be a Vim version, I'm not sure. It supports the full Erlang language, so it's not one of these tools that only works with a subset or with, you know, if the wind's blowing east or whatever. It'll work for the full Erlang language. It's also faithful to your laid down comments, so it won't produce code that you won't understand. It's very important. If you're programming a particular layout, it will try its best to preserve that type of style. It has an undo. I've talked about that briefly, so you can go back, obviously. And it's built in Erlang, but that's not really that. And here's an example of a screenshot here of Wrangler built into Emacs. So what we've done is we've taken this idea of having parallel patterns and the refactoring tool, and we've kind of bolted them together. And the idea of what we come up with here is a methodology. So this is a disciplined, if you like, software engineering kind of way of thinking. It's much more structured than just randomly using Erlang processes and spawns and receives all over the place. So the idea is you start off here on the left, this white box. It says sequential program, but it really doesn't matter. You start off with a program, basically. It could be parallel, it could be sequential, doesn't matter. Then you look at that program and you gain some evidence about it. So you look at the structure of the program. So you have to do a little bit of thinking. What is the program doing? How is it doing it? Okay. And then what you can do is you can use a cost model, which I'll describe very shortly. So you can get some information about how long particular parts of your code are running, what structures give you what performance information, this kind of thing. And then you can use our refactoring tool to introduce your parallelism. So once you've identified the structure, you can just use the tool to introduce the parallelism for you. And the result of this is the thing on the right, a parallel program, hopefully, with some introduced skeletons. You can then execute this. If it doesn't give you the result you wanted, or a new chip comes along, you can simply just try a different one, try a different refactoring, etc. And then you go around and keep going. So we've purposely done this so it's not a compiler. It's not a magic box that just generates code. Okay, those things basically don't work. Compilers that generate parallel code have been around for a long time, probably since the 70s or the 80s, and they don't work. They work for an incredibly limited set of examples, introduce very simple types of parallelism. But what we've got here, we want to take any kind of program, doesn't matter what, we want to introduce parallelism. It's a whole completely different league of problem space. So these are just some examples. So refactoring is it's not just an ad hoc thing. It does have some science behind it. I'll just go over these very, very briefly. So there are rules that exist out there that kind of help us choose what kind of refactorings we're going to implement. These rules here are taken from the skeleton community. Been around for a long time. They're quite well known in that community. But what they say is if you take the thing on the left, you can basically rewrite it into the thing on the right. So these are like refactorings, if you like, just a higher level of refactoring. So what this first rule says, if I have a composition, so I apply S1 to S2, I can rewrite that into a pipeline where I have two stages, S1 and S2. So obviously it's quite obvious. Another example here, if I have a map where I have the worker function as a composition of two things, I can rewrite this. So I put the composition on the outside, and so on and so forth. So depending on what your application does, depending on what the cost models come back with, all of this kind of stuff will indicate which one of these things you should choose. Because not in all instances choosing the same rule will always give you the best performance. is very important. We also define our refactorings just in a kind of semi-formal way. So I said before that refactorings are a transformation and a condition. So what we've got here is just a way of kind of describing what they are. So this thing here, with the quasi quotes, is like a function. Just think of it as a function that takes an expression and transforms it into another expression. And refactorings can have subrules. You can chain them. You can do choices, all sorts of things. So this is just an example of what these rules look like. So this rule here is called pipe comp. It takes an environment and an expression. So this is the thing that the programmer selected. They selected this expression and they want to introduce some kind of parallelism. So this bit at the top line says, I want to match, if the thing that the user selected matches it, so if it's basically a list comprehension, where it's got a function application here, I can simply refactor this into a call to Skel with a pipeline. And then we've got some conditions down here, so we check that things are in scope, etc., etc. Just another example here, I've got something a bit different. In this example, I've got an already existing skeleton, and I want to rewrite that skeleton into a pipeline. So this rule just says if I match something that looks like this, I can rewrite it into this pipeline. And then again, I have some conditions here. So this transformation will only proceed if these conditions are met. And this is just an example of what these refactorings actually do. So here at the top of the slide, this is just an example piece of Erlang. So the user's written some function, some list comprehension with some function applications here. If he selects this in our refactoring tool, it will rewrite it. If he wants to introduce a pipeline, it will rewrite it to the thing on the bottom, where he has a call to Skel with a pipeline, where each of these functions becomes a different stage of the pipeline. Okay. So it might look trivial to you, but what's interesting is about 2 years ago at the EUC conference, we ran a tutorial on this, and most of the audience are quite experienced Erlang programmers. And firstly, what we got them to do is to take the manual code and rewrite it into this. And the amount of errors they got just trying to run the thing was crazy. You know, you miss a brace off, you miss a bracket, whatever, you get the function wrong. Just doing this automatically saves huge amounts of time, really does. And this is a very simple case, very, very simple case. So we have a number of these refactorings implemented. So we've got things like we can introduce and eliminate pipelines, farms, all sorts of things. We can do some chunking. So this is optimization refactoring that allows you to kind of group together tasks to make the parallelism more coarse-grained. So this is good if your computations are very small. So you want to make them as large as possible to get the most performance. This is like a tuning refactoring. And they're all reversible. So if you introduce something, you can always go back. So you don't need to worry about making a mistake. I mentioned, before I mentioned cost models. And so one thing that's important with these tools is, obviously you can introduce the parallelism, but how do you know which one to introduce? How do you know what refactoring you're supposed to apply? Okay, we don't want it to just be kind of like a magic black box. We want to actually inform the programmer in some way about what they're supposed to be doing. So what we did was we developed some very high-level cost models. So these are models that are not intended to be completely accurate. They're just supposed to give you an idea of what your performance is going to be if you choose a particular refactoring. It's almost impossible to get these 100% accurate anyway. So just quickly describe what these mean. The top one, this tells you if you have a pipeline, you can basically predict the performance as roughly the maximum of the pipeline stages. So whatever your slowest stage is, that'll be roughly what your pipeline performance will be, plus some time to copy. The map is slightly different. So you take all your workers and you divide it by whatever's smaller, the number of workers or the number of CPUs you're running it on, plus some time to send your tasks out and some time to get your tasks back. So this gives you rough estimates. Farm is slightly different. The farm, you basically do the same thing. So you take the cost of one worker, you divide that by how many you've got, and you take the maximum amount of time between how long it takes to send an item out, how long it takes to send an item back, and how long it takes to compute. This gives you a very rough estimation. So just to show you an example here, this is a denoising example. The idea is you take a picture with some noise in it. It could be a satellite image or a TV picture or whatever, and you try and filter it to get back some of the original image. So the algorithm is very simple. So here we just have a simple function. What's important here, I just wanted to show you the point of this example, is that the structure of it's been identified. So the programmer has identified that this thing has some structure. The original code might not necessarily look like this. It's just to show you as an example. So you've got some functionality here where you've got two functions. You do some georeferencing, and then you do some filtering for a bunch of images that are coming in a stream. And this is your denoising function. So I want to refactor this. I want to introduce some parallelism. But how on earth am I going to do that? When there's so many different possibilities I could do here. So what I've got here is just an example. This is just, these numbers here are just using the cost models. So in this example, the first step I'm going to do is take that and introduce a pipeline. And I can do that because my refactoring tool tells me it's the best choice. Because it says, if you've got a composition, which is basically what this is, so I've got two functions, filter and georef, it's going to be roughly this time. Because I take the worst time for each function and divide it by, I multiply it by how many images I've got. It's going to take this amount of time overall. If I introduce a pipeline, it's going to reduce to this. So it's going to go from 65 to 47, just if I introduce a pipeline. So I think, okay, I'll do that. So I select this piece of code, and the tool gives me back this skeleton thing. And then I run it, and I get a decent performance. But then I can tune it quite dramatically after that. So once I've got this pipeline stage that the refactoring tool has given me, I can then go on and tune it. And in this case, so it's saying, okay, the pipeline estimation is going to take this time, but if you introduce a farm, or a map in this case, you're going to get it down to this. So it's going to go from 47 to 17. That's quite good. It's okay, I'll do that, I think. And then the last stage of this refactoring, I'm going to even optimize it even further. So I'm going to go from 17 down here to about 2. So I'm going to take my code that the refactoring tool introduced, I'm going to refactor it even more to introduce a farm here in the first stage, and I get it down from 17 to 2. So this is just a summary of that kind of process here. And what this graph's showing is along the bottom, this is the number of cores. So from 1 to 24 in this particular case, running on a 24-core machine. Going up on this side is the speed up. So this is how many times faster this is running against the original sequential version. And the blue line indicates the very first step we did was just introduce a simple pipeline. So we just took our composition and made it a pipeline. We do get some speed up, just over 1. It's not very good. Also, the dotted lines here show this is what the cost models were predicting. So in this case, it's almost exactly what the cost model predicted. The solid red line, this one here, is the second stage, so we introduce a map into the second part of the pipeline. We get a bit of a boost in performance, so it goes up to about 4, but then it flattens off. So it's still not very good. And then this version here, the kind of the light brown color, this is when we go to the final stage where we also put a farm in the first stage of the pipeline. And as you can see, this kind of scales all the way up almost. So we get about a speed of about 18 on 24 cores, which is pretty good. It's also pretty good because all the users had to do is click a few buttons. He hasn't had to actually implement anything. He just selected a piece of code and introduced some patterns. It's a 2-minute process. So going from this to this with a few clicks of a button is I think is pretty good. This is just another example. This is called a sum Euler. This is just a very simple example from computer algebra. The point here I wanted to show you was with the blue line here, it kind of starts to tail off a bit here. And this is just using a simple farm pattern. So the user's just introduced a farm, but it's kind of tailing off. And he's got a 24-core machine. He's getting about a 16 speed up. Still good, but he can do better. So what the tool comes back with and says, if you use chunking, so if you group your tasks into groups of 400, you're going to get a kind of a speed up of here. So you're going to get linear speed up. So he does that, and in reality it's close, but it's not exactly there. So it's about 22 speed up. So that's pretty impressive, I think. So this is an example of effort. So I talk about performance. The tool delivers in performance, but how does it deliver in effort? What we have here is just a table of different use cases that we've given to some industrial contacts that we have. And so convolution is a simple example. It's very similar to the denoising one I've just shown you. These are actually done in C++, not Erlang. We have tools for C++ that do similar things, but the principle is the same. So it took these guys, for convolution, about 3 days to write the parallel implementation from scratch by hand. And these people are fairly, I would say they were experts in doing this. So for them it went from 3 days to about 3 hours. And that includes the time it takes to actually understand how to use the tool as well. In this example here, and Colony, it went from something like a day to an hour. This one is probably the most impressive. The basic N2, this is a molecular dynamics use case. It's about something to do with tracing how molecules interact with each other in gases. It's quite a complex use case, but it went from something like 5 days of implementation down to 5 hours. So obviously this is not just about performance, it's about effort. It's going to save companies millions of pounds in effort using tools like this. And obviously, if you're saving on effort, you can increase effort in other places. So you can concentrate on making sure your software is doing what it's supposed to do, rather than optimizing it. So that's the basic idea of refactoring. So using refactoring tool to introduce these patterns. But there's something else I wanted to talk about, and that's called program shaping. So all of the examples I've shown you here are pretty easy. They're pretty simple. Okay. In reality, programs don't really look like that. They don't look as simple as that, obviously. And you have other problems, such as extra functional properties like memory usage, this kind of thing. So another kind of dimension to refactoring is something called program shaping. The idea of this is that it's another refactoring step that you can perform before or after you've introduced your parallelism. So it can be done to get the program in what we call a shape. So you might have programs with lots of dependencies, you might have code all over the place. So you can use refactoring to break those dependencies or tidy your code up, or to make it into a way that then you can just simply introduce your skeletons. Okay. It also does other things like you can improve your memory usage by transforming different data types, like lists into binaries, and this kind of thing, to reduce copying. And it does all sorts of different things. This is just a simple example again. Does anybody know who this is? I know it's a bit small, the image, but... Sorry?
Simon Peyton-Jones?
No, it's not Simon Peyton-Jones, no, close. But Joe Armstrong, yes. Yeah. So Joe Armstrong's the co-inventor of Erlang, in case anybody hasn't met him. Anyway, the point of this example is we've got some images coming in, and we want to merge the two images. So we want to take this image with this image and put them together. So what we do is we take the first image and we make all the black pixels white. Then we simply, in this stage, we take each white pixel in here and replace it with a pixel from this image. So it's a very simple image merging example. So here we put the Viking hat on Joel's head because he lives in Sweden. So it was nice, appropriate. So this is the basic code. You don't really need to care about what it does. It's not really that important. The main part of the code is here. You have 3 stages. You read an image, you do some conversion and merging, then you write it out. Okay, so it's quite simple. So what we do first is we go through our refactoring steps that we did in the first part of the talk. So I first introduce a pipeline here. I make each thing a parallel stage, so read and convert, merge, or parallel. And then I do some refinement, so then I introduce a farm. So I take the second part, the reading parts, and introduce a farm. And then I do the same for the second stage. So the result is a pipeline where each stage is a farm. So this should give me good speedups, right? No. So we ran this on a machine. The reason I have Sinking of the Titanic is because the particular machine we're running it on is called Titanic. It's a very appropriate name for a multi-core server. Okay, basically it crashed. It didn't work. We didn't get any results whatsoever from this code. Can anybody think why?
Locks.
Not locks, no. No, not close, but no. So the reason is that it's memory bound. So this implementation uses lists in Erlang, and lists in Erlang are horribly inefficient. If anybody has ever used them, and they're horribly memory bound. The problem actually is not necessarily that they are memory bound in themselves, but the problem is you've got so many images coming in, and each time you pass the image to a worker, you have to copy it. So you get huge replication in your images. And if you've got thousands of images coming in, you're going to end up with millions of images floating about. It's horrible. So you just run out of memory trying to run this thing. So you might think you've got the most efficient implementation, but you can't run it. So it's a bit pointless. So what we've got is some refactorings that kind of get past this hurdle. So example is list to binary. So you can take these lists and make them binary. And binaries in Erlang are basically pointers. So instead of copying the list, you just copy a pointer. Much more efficient. You can convert it to an ETS. ETS is like a mutable type of thing. And you can convert binaries to ETS. It's like an updatable table. What I'm going to show you today is just the list to binary. So I can go back to my code, and I can take the bits, and the refactoring tool will just rewrite them. So it'll just take the list implementation, rewrite it to a binary implementation. It'll do that through all of the code, wherever it's referenced. So it does it here again. It also does it, not only does it do in the pattern matches, but it does it inside the function bodies as well. And the results are actually much better. So I can actually run it now. So what we got here, this is all using a binary version. The red line here is just using a simple 2-stage pipeline. There's no data parallelism there. Obviously, it flattens out. It's not very good. The next one is the kind of the blue line. That's the best one. So that's our pipeline with 2 farms. That's what the refactoring tool wanted us to do. But actually, it was the best, but we just used the wrong type of implementation, wrong data type. These other lines, the black one was a manual implementation, but this manual implementation is not a naive one. It wasn't just spawning millions of processes. It was done in a reasonably controlled way. And it's actually quite close. It's not bad. And the green one is a farm where each worker is a pipeline. So it's kind of the opposite. It's the inversion of the best one. It's also not bad. What also this shows is that the tool is comparable to a manual, to a good manual implementation. So we're not trying to show our tools will always give the best, but they are within the best, if that makes sense. So really the last thing I just wanted to talk about today is how do we know these things are right? So one thing I've kind of said at the start of the talk, that a refactoring tool won't introduce code that's incorrect. That gives you code that's wrong, that won't run, and that gives you wrong results. There's lots of ways to do this. One way that we've tried to do this is to show it using basically equational reasoning. So this gives us a soundness. This gives us a guarantee or some guarantee that these things are doing what they're supposed to be doing. I just wanted to very briefly talk about how we're doing that. So what we've got here on this slide is some functional semantics for our skeleton implementation. And by functional, I just mean they're simple functions. So we've taken things like spawn. So our skeleton's implemented in Erlang. So we've taken Erlang abstractions like spawn and send and just made a very simple functional behavior for what they do. So we have things like spawn, send. We've got our Skel do, which is defined in terms of spawns and receives. This is an emitter for a farm. And once we've got this base functional semantics, we can basically take our sequential program. So this is a very simple sequential. What this is showing is if you've got some function f that is applied to some input, you can eventually rewrite it until you get a map or you can get a farm. So you can simply do that by taking your definition of Skel do, inlining it until you get this, inlining that again until you get the lambda here, and so on and so on and so on, and then eventually you get this map f at the bottom. So you're basically just a very systematic process of taking the input and the output from the tool and trying to get from one to the other, doing simple functional rewriting. Okay, so that gives us just a guarantee that our tool is actually doing what it's supposed to do, which is very important. I'm just going to briefly mention also, the title of my talk said heterogeneity, but I haven't really talked about that. Vladimir in the next talk will go into a lot more detail about how we do heterogeneous computing for Erlang, so how we do offloading to GPUs and things like that. Part of that work is that we've extended our skeleton library, so our Skel framework, to include offloading. So you can also have parts of your skeletal pattern that work on GPUs or whatever device you want, and Skel basically does all the offloading for you. So it works out the correct ratio of tasks to offload and so on and so forth. I'll let Vladimir go into that in much more detail. So we call these hybrid skeletons, so i.e. a mixture of CPU and GPU skeletons. But we also have refactorings that work with these as well. So this is just an example here. So I've got at the top here, this is my original code. So I first refactor it, not using any hybrid stuff. I just do a normal introduce map refactoring. The result of that gives me a simple parallel program, and then I can introduce a hybrid. I can introduce a GPU component. So if I have a CPU component and I have a GPU version of that, I can simply extend it to be a map where it can dispatch tasks to both a CPU and a GPU worker as well. We're currently working on ways that you can generate this GPU component. So that's currently in progress, but the rest of the framework is in place. Now this is just some very preliminary results, just to show you what our hybrid versions are doing. So here we've got the blue line. It's a simple binary version. This is image merge again. This is the same one where we put the hat on Joe's head I showed you before. So the blue line is just a simple binary version. We slightly improve it with our binary to ETS refactoring. It gives it a slight improvement, but not much. But if we use our hybrid implementation, so this is also using a GPU to offload tasks in addition to using the CPUs, we actually get quite a big difference here. So it goes from something like, so that must be about 12 to 14, something like that. So you get that kind of boost of performance, which is quite nice. So if you've got a server with a GPU in it, you may as well use it to get some performance. And this can be the difference between days and hours for some systems. So just in conclusion, hopefully I've motivated why you'd want to use refactoring. We think it's a great idea because it guides a program through all the steps they need to parallelize a program. It's not just a blind, let's hack some code type approach. It's much more disciplined. You can have all sorts of nice things in a tool. You can warn a user if they're doing something stupid. So obviously if you introduce a pattern that's going to give you slowdown, you don't want to do that. So a tool will inform you that you're doing something wrong. It avoids all the common problems with parallel programming, getting your head in spaghetti locks with all these processes and messages and things. It's just a nightmare to deal with. It helps with an overall understanding and intuition with writing parallel code. So I go back to this idea of compilers that generate code. The other reason you don't want to do that is because you don't know what it's doing. If you've got production software, you don't want some black box magically changing your code. It's not really very good. So a refactoring tool is completely transparent. So the tool it produces, it's not hidden, it's not lying what it's producing. Skeletons reduce boilerplate is another nice property. I mean, functional programming is all about high-order functions. You don't want to have lots of boilerplate code everywhere, kind of the whole point of it. So it allows you to concentrate on getting your program right rather than its implementation. So it kind of motivates that message of functional programming nicely, I think. I'll just flash up the funding slide. Just this one point before I finish. We need people, basically, to help us with this. So if you have any ideas, you have any programs you want to try with our tools, anything, any ideas, suggestions, please get in touch, because we'd love to hear from you. We have a mailing list that you can join if you like. You can get all sorts of news and updates on our tool progress. We've got things like developer workshops you can go to. You can help us develop the tool if you want. Very, very welcome to have people help us. We have tools for Erlang and C++, so if you like other languages, you like more imperative languages, don't be shy. Come and talk to us. We want to hear from you. That's basically all I had to say anyway, but thank you very much for listening.
Thank you, Chris. Do we have any questions?
So I have a question. One thing I don't understand is it sounds like this could be really affected by something like a hill climbing problem. Like you find basically a local optimum, local maximum, right? So do you guys backtrack and maybe try things that the cost model doesn't predict is the best solution? Or how do you comment that situation?
Yeah, so the question was, can we use some kind of optimization or heuristic to kind of get what's the optimal refactoring or the optimal configuration? The answer is yes, we do that. In fact, we have a paper. We have one paper that uses not hill climbing but Monte Carlo, which is another optimization to get to the optimal point. We're also in the process of writing a paper that uses hill climbing, Monte Carlo, random searching, and various other techniques and tries to compare them to see which one's the best. So you can use things like optimization heuristics, not just for choosing the right refactoring, but also choosing a mapping. So I talked before about hybrid skeletons have CPU and GPU components. How do you know how much of your data to send to a CPU and how much to send to a GPU? It's a non-trivial problem. So one example of an optimization heuristic is it can give you back the optimal mapping you need. Then that information can then be fed into the tool.
I'm not even sure if the question if it makes sense, but do you also do things like fusion refactoring, so that you typical taking a map of time after G is these kind of refactorings?
Yes, we do. I haven't described any of that kind of stuff here. I believe Wrangler has built in. I think it probably might have fusion, list of fusion built in. But we're certainly aware of those types of optimizations, and that wouldn't be a problem to apply them here. Yeah.
Any more questions? So thank you again.